Thank you. First, thanks to the organizers for this wonderful conference. Always good to be back to Stockholm. So, yeah, I mean, since I only have 10 minutes, so I just decided to advertise a couple of directions that I've recently become very interested in. So, we really know no details. So, we heard a lot about CMB experiments, current and future. But we should remind ourselves that there will be a lot of experiments also for the low redshift that are coming soon, also in the future. I just showed a couple of pictures, so especially Euclid and the SKA that I'm personally involved in, but will provide tons of data and all having valuable information that we can use for basically doing cosmology. So it's really important to keep in mind. So let me just show you this typical kind of power spectrum of the matter that you have in the universe. So you have different scales, and so in principle you have two main regimes. You have a regime that you can apply a linear perturbation theory structure formation, and also you have these very small scales that you have to do nonlinear. And in particular, I'm focusing on these two ends of the spectrum, the nonlinear and this other side, which is linear, but it's called ultra-large scales. And thanks to Theo, he actually yesterday motivated us why it's very important to look into the very large scales or ultra large scales. But in particular, what I would like to mention here is that like the focus here is on the modified gravity side and the alternatives to gravity theories that have been many models have been developed recently in order to explain the cosmic the relay time cosmic acceleration. It's this beautiful plot made by Professor Baker, published in this paper that we put out a year ago. And so, just for a couple of seconds, you can enjoy this and see, I mean, the level of imagination here is comparable to population community. So it's really not, you're not missing any or lacking any really framework. So I just refer you to Lavinia's talk tomorrow, maybe for a more overview of these models. But I just wanted to say it's very important to test these things, and in principle we can do it with all these low redshift servers. Also, I wanted to just mention one more thing, which is more related to this conference for early universe stuff. So I just wanted to say that it's not only modifying gravity directly in the infrared, as I showed you before, or to get acceleration. You can also get models that are coming from early universe stuff, so inflationary models. For example, in this beautiful framework of alpha attractors that Andre and Renata actually collaborators developed. So I don't want to, of course, talk about this, but just refer you to the talk by Renata and Andre later on. So these models actually really provide very nice fit to the early universe data, to the CMB data. And just wanted to say that you can basically use these models also to get late time acceleration. For example, this paper of Dimopoulos and Owen recent paper, actually you can see that this is doable. At the moment, with Andre and Renato, we're trying to see what we can do, basically maybe better than this, or in the framework of the recent developments that they have done in this field. So really, these are very important. Yeah, just mention again Andre and Renato's talk. So, one point here is to show you this plot of the contribution. This is the ultra large scale part. So you see that, for example, the angular power spectrum of the largest structure, there are really like features that can come from modifications to gravity or like dark energy and stuff like that on very large scales. That these are very important to look into. This is a paper by Baker and Bull, which is a very nice paper. So also on the other side of the spectrum, for nonlinear spectrum, you see, for example, that there are effects that are coming from, for example, these are the F-bar theories. So you see that it really is important to measure this side of the spectrum too. So with this, let me just tell you that for this region that is actually linear and quasi-linear region, there are lots of codes at the moment on the market. I mean, high class, Miguel is here. If you have questions, you can ask him. And for EFT-CAM and Cosmic Fish, Matteo is here, can tell you more. So there are lots of actually codes developed for this. But for nonlinear part, I mean, the main thing that we do these days is simulations. And also there are some analytical kind of ways of doing this, like EFT of LSS. Leonardo is here, can tell you about that. So this is really what we do. For the ultra larger scales, you can still use this linear basically code, but the thing is that we have really not much data here, because of the cosmic variance. So we need to beat cosmic variance, maybe using multi-tracer approaches and so on. So these two ends actually got two main problems. Here we don't have much data. Here we have regular simulations, which are very hard to do. Show you one plot of this paper by Miguel and collaborators for the next generation of experiments, that you see that you can do a lot of things for the ultra large scales. These are basically some parameters of this class of modified gravity, we call it Mordensky, some kind of computation of that. And at the moment, with my collaborators, we are looking at basically what we can do for this ultra large scales. For example, apply this framework, basically this data to the EFT of dark energy and modified gravity. Also doing some stereo optimization for the upcoming and also the next generation of experiments, which is very important to know how to do this in order to detect all these effects. Also, it's important to understand what are the effects of the different approximations one makes, this set of like Limbaugh approximation, relativistic effects and all that. So this is an ongoing project and long project. Right. Just for the other side of the spectrum, I mentioned that we need to do simulations, but it's computationally really expensive. That's the main problem with this. And we have lots of models, lots of parameters, and we cannot just go and do the simulation for H1. It takes like months for H1 to be done. So I just wanted to advertise one framework here that I've become very interested in recently. I know this is very controversial actually in the community at the moment, but we try to understand this. This is a framework. It's called Kinetic Theory of Large Structure, developed by Matthias Waltermann and collaborators in Heidelberg. So I'm not going to go through these details, of course, here, but I can just tell you that this slide shows you really the main kind of steps that you can make. It's based on this statistical mechanics framework. You basically have some partition functions and then some operators, and you can calculate interactions in this case, and then calculate all the endpoint correlations that you might want, like power spectrum, time spectrum, bispectrum, all this stuff. So the main thing here is this interaction between two particles, like really like a simple interaction, this potential between the two that you plug in here, and then you can get to the first order, the nonlinear power spectrum, which is I can tell you that this is a very complicated framework. This is notations are actually really difficult to understand. We spend like months talking to Matthias all the time, but if you understand this, I can say that arguably this is a super beautiful framework, and it's very powerful. This is one example that they had in their original paper of how they can get this nonlinear thing with just one step in perturbations. And well, this is some approximation. That's why you see that compared to simulations, you still have some discrepancies. But this is because there was some approximations involved. But now with the recent developments, you can really do better when you take into account the full hierarchy of momentum correlations. And there are lots of advantages for this. It really takes a few seconds to calculate these things. It already works at first order interactions. It's very accurate. Gives you some insights. For example, where or when the transition from linear to nonlinear regime happens. And also, it's very easy to modify. So we are trying to use this one basically to develop this for modified gravity and daytime cosmology, which I think I'm actually quite excited about this. Well, so this is what we are doing now with my collaborators currently. So yeah, just to summarize, we'll have a lot of data provided soon by all these daytime experiments, and there is a lot of information basically in this ultra large scale and also small scales that we need to extract and also use properly. So this is very important to test models beyond the standard model, whatever you are interested in. So there are lots of codes and techniques developed, but still it's a lot to do, a lot left to do. And I just wanted to, so this is the last thing, so I wanted to advertise this framework, which I think is very interesting and really will do a lot for us if it's true. Thank you very much.
Thank you.